Hey, it's Steven, and this is my project, A Runner's Speed is a Function of Their Cadence and Stride Lengths. In this project, I will talk about what a function is, use of functions to solve problems related to famous runners, and create my own data in an experiment. But first, a little background information about myself. So, I started doing track about a year ago, but I've always loved running because when I played soccer, I was always the fast kid. And if I'm being real, I love the running aspect of soccer a lot more than kicking the ball around. I wasn't always the fastest in an all-out sprint, but I could not tire out as much as some of the other kids, which gave me an advantage playing midfield. Basically, running is a sport of hard work because it hurts a lot. So you have to stick with it and you have to, be positive with yourself and work through it mentally. I've met a lot of good people doing running, and that's probably my favorite thing about running. The equation, stride lengths times cadence equals speed. This means that a runner's speed is a function of their stride length and cadence. Any two of the three variables can be used to find the unknown variable. For example, cadence will equal speed divided by stride lengths, and stride lengths will equal speed divided by cadence. And for those of you who don't know, cadence is actually steps per minute. Using data from famous runner Eliud Kipchoge. So on September 16th, 2018 in Berlin, Germany, Eliud Kipchoge ran the world record for the marathon distance. His time was 2 hours, 1 minute, and 39 seconds. Knowing that speed is distance divided by time, we can equate that Eliud ran at a speed of 42.2 kilometers divided by 121.65 minutes, which equals 0.34 kilometers per minute. Then we're going to times 0.3 kilometers per minute times 60 to find his hourly speed rate. When we do that, we get 20.4 kilometers an hour. So that's his speed. Calculating pace. Calculating pace is actually the inverse equation of calculating speed. So while speed is distance divided by time, pace is going to be time divided by distance. Using Kipchoge's world record as an example, we can do this. 121.65 minutes, which is the time, divided by the distance of 42.2 kilometers, we get that he ran 2.8827 minutes a kilometer on average over the race. That was his pace. So 2.8827 times 60 is going to equal 172.96, which is equal to 2 minutes and 53 seconds per kilometer. One thing that's really important when we're doing conversions like this is that everything is in the same units. You don't want to mix the metric system and other systems. You want to have everything in meters so that it's very easy to convert. So, creating a function. In math, a function is a pair of inputs and outputs. In a function, each input has only one output paired to it. In my running functions chart, everything on the right is a function of the variables on the left, except the last one. So, the chart on the left here, I think, is a very good example of what a function is. As you can see, every input, everything under the x, is paired with one output. So 1 is paired with D, 2 is paired with C, and 3 is also paired with C. It doesn't matter that the two inputs are paired to the same output, as long as they're only paired to that one output. So you could say that D is a function of 1, C is a function of 2 and 3. The same way that you could say speed is a function of stride lengths and cadence on my chart. Speed is also a function of distance and time, and cadence is a function of speed and stride lengths. Now, contrary to popular belief, cost of shoes, speed is not a function of cost of shoes. This is because you can get different outputs. In a function, your input predicts the output, but with cost of shoes, that's not going to predict the output because you could have multiple results. Contrary to distance divided by time, when you put in correct data for, distance and time, you're always going to get the same speed. Speed divided by stride lengths will always create the same cadence, but, cost of shoes will not always have the same speed, creating multiple outputs, which makes it not a function. Functions continued. So let's do an easy example. But first, f of x equals y is the general expression of a function, where x is the input, y is the output, and f is the function. An easy example is f of x equals y when the function is x plus 4. So when the input x is 3, and we put it through the function, which is x plus 4, we get 7 because f of 3 equals 7. Now a challenging question using functions. Using the principle of functions, determine a runner's cadence if their pace is 3 minutes 20 per kilometer and their stride length is 1.8 meters. Personally, I chose this question because I think it's about my stride length maybe, and I run 3:20 a kilometer when I do my 3Ks. Let's set up the equation. F of x equals y. We know that x is the input. So the function of our input, cadence times stride length, equals our output, which is going to be speed. So the function of cadence, which is unknown, times 1.8 meters equals 320 a kilometer. Then I converted 320 a kilometer to seconds. So 180 is 3 minutes plus 20 seconds, 200 seconds. And I know that distance over time equals speed. So I did 1,000 meters covered in 200 seconds equals 5 meters a second. Then 5 meters a second times 60 seconds creates 300 meters a minute. So now I have a simplified equation in doable units. The function of cadence times 1.8 meters equals 300 meters a minute. Cadence times 1.8 meters is going to equal 300 meters a minute. So to single out cadence, I have to divide each side by 1.8 meters. So I do 300 meters divided by 1.8 meters to find that if my stride length was 1.8 meters and I was running at a 3 minute 20 kilometer pace, then my cadence would be 166.67. So in this question, we had to convert pace to speed. Next, let's take data from the pros. Mo Farah ran 27:30 for the Olympics 10K in London 2012. His stride length was reported at 2.18 meters, and his cadence I couldn't find on the internet. But we can solve it with the data we do know. We know that stride length times cadence will equal speed. So first we find the speed so that we have two variables to find the cadence. We can find the speed by dividing distance by time. 10,000 meters divided by 1,650 seconds, which is 27 minutes, 30 seconds. And I found that he took 6.06 meters per second of distance covered. Then 2.18 meters times our x value equals 6.060 meters. So then I did 6.060 divided by his stride length, 2.18, to find that he took 2.779 steps per second. Then times that by 60 to get 166.788 steps per minute. And cadence is always in steps per minute, so that's how we want it. Now, I wrote this down. Honestly, I would be surprised if his cadence was actually that low. Considering he's an Olympic runner. I think that his stride length was actually overreported, but who knows? If you look up a video of Mo Farah running, he does have quite a long stride. Either way, this process is helpful and accurate for finding the number of cadence or stride lengths, but it does, you do need like correct data to get, correct equation, but the equation will always give you reliable data. Finally, let's use Eliud Kipchoge. He ran 2:01:39 at the Berlin Marathon. His stride was reportedly 1.89 meters, which I think is more realistic, with a cadence of 185, which also seems realistic. We can check this data for accuracy by calculating his speed the most accurate way, distance divided by time, then comparing it to the stride length times cadence. Okay, so first I did distance divided by time, which is the most accurate way to find speed. His distance was 42.2 kilometers divided by time, 7,299 seconds. And I got 5.781 meters per second times 3,600, which is seconds in an hour, equals 20.813 kilometers an hour. Now let's check for accuracy by doing it with the reported stride lengths and cadence. 1.89 meters, which was his average, lengths of step, times the amount of steps he takes per minute, times 60 minutes. So that's going to get his distance traveled in an hour. And I got 20.979 kilometers an hour. So as you can see, very close. So obviously the 20.813 is the most accurate way to find distance because it's distance over time. But both numbers are within 200 meters, meaning that, with a little rounding, I believe that the cadence and stride lengths provided were very accurate. Finally, let's talk about my experiment. So I thought it'd be pretty cool to observe my own data because I'm a runner myself. So I went out to the track and recorded a lot of data, like heart rate and steps and stuff, using my fitness watch, which is the Garmin Forerunner 45, at 3 different paces: 8-minute mile, 7-minute mile, and 6-minute mile. What I found was kind of what I expected, but it was so perfect, to what I expected, that it made me want to create a graph, which I did in the next few slides, so stay tuned. All right, so there's a few trends in the data that I think you should notice. So when I did my 750 mile, I took more steps than when I was doing my 7 and 6-minute mile. And obviously my heart rate went up, that's expected, but what I want you to notice is how the cadence goes up only 9 steps per minute over the course of dropping 2 minutes off my mile time. However, my stride lengths, which during an 8-minute mile was 1.26 meters, jumps to 1.39 meters when I do a 7-minute mile, and then all the way to 1.58 meters when I do a 6-minute mile. This is quite significant, and it's actually pretty cool to see that really my cadence didn't increase that much, but really I'm just lengthening my stride when I need to get faster. And I think that's pretty cool to see that data in action by doing math. So I read some articles on this and they were all saying the same thing. But basically what we found is that my stride lengths had a 300% higher increase relative to my cadence. So really, when you're getting faster, your cadence is improving a little bit, but mostly you're just lengthening your stride. All this data was found using the functions. I had to obviously do this all myself. I don't have a cadence feature on my watch or a stride length feature, but I was able to use my steps and time to calculate all these. And what I find interesting is Garmin and Fitbit and stuff, they'll charge more for watches with features like stride lengths and cadence. But, those can actually be less accurate than just doing the math, because the math is always going to give you an exact number. So, yeah, team math, I guess. All right, here's where I graphed my data of stride lengths versus kilometers per hour. Now, this is really cool to see how linear this line is. Look at how straight it is. I know I did a smooth graph, but you can see, it's not spiking at all. My stride length is increasing at a very good steady rate as my kilometers an hour goes from 12.2 to over 16. Now let's compare that to how my cadence is affected as my kilometers per hour goes up. Now, these graphs are a little confusing because if you just look at them, you're going to think, oh, wow, the cadence is spiking at a lot higher rate than the stride lengths. But obviously that's wrong from my big chart. The reason it appears like this is because my stride lengths Excel spreadsheet wanted to start at 0 for the stride lengths, while the cadence, actually worked and was able to start at 161. But so actually, if cadence and stride lengths were on the same graph, you'd see actually a much lower rate for the cadence increase. But still, it gives you a good idea again of how linear this line is and how straight it is, and how evenly the cadence increases as your distance increases. It doesn't jump crazily. Different paces and more. Honestly, I just found these interesting charts. The first chart you can look at, it's all the different ways to run different paces. And I found it fascinating how when you shorten your stride just a little bit, just, 18 centimeters, now you have to take 30 more steps per minute, which is quite significant. Also, I found this chart on the right cool because it shows the relationship between pace and stride times cadence in a percentage manner. Percentage increase in cadence plus percentage increase in stride lengths is going to equal the overall percentage increase in pace and speed, which is a cool way to think about it. My concluding thoughts. I actually had a lot of fun putting together this project and doing my experiment. I learned a lot about data patterns, percentages, functions, and more. Most importantly, I learned more about the relationship between my running and math. Both big passions of mine, but okay, that's just a joke. But anyways, thanks for watching. But honestly, I like this project because I found it cool, like relating my running, which is a big passion of mine, to math and actually finding, the data was interesting and not just boring. But yeah, I had a blast doing this project. And this is my bibliography. Thank you for watching.